Okay. My phone isn't on now, so
Okay.
but at least you'll have it.
Yes. Just to touch. Maybe we meet somewhere.
And inshallah,
Yeah.
yes.
Maybe renting the club, club or something.
Yes, this would be nice.
Yeah, for sure. My kids over there, so
Okay.
we can meet over there.
Inshallah.
Inshallah. Okay.
Okay, so what did you say? I need to share something? I just want you to. Oh, okay, do we have a marker pen? I guess that we start. I guess you have to choose so last time we were talking about we looked at some different situations, different kinds of reactions. We saw some of the solutions. Example, exponential decay, and we have exponential zero, for example, decay, and you have an exponential approach to a steady state. When you also have reduction of decay, and then if you have reversible conversion, then you have an exponential approach to a final steady state. So, and then we look at the Phillips method inside methods, and we saw this curve where for a low concentration of substrate, we have a linear rate with substrate concentration, and then it levels off. And then we saw that we have heating reaction, like, and that there's actually different kinds of inhibitions, called buffer inhibition. And the buffer inhibition, that means that the inhibitor of the substrate will bind to the enzyme, but once the inhibitor is out, then there will be no substrate on the bottom produced. So in this case, the rate, the initial rate is still linear, but the plateau, the steady state rate is reduced. And the more inhibitor it is, the greater reduction in this plateau. And there's one other example I want to look at before we start visualizing some of these situations using the base ordinates, and that is cooperativity. So we already saw an example of cooperativity last time. Does anyone remember the example of cooperativity that we looked at last time? Where we were talking about link equilibria, remember we had this model for link equilibria, and we chose hemoglobin. So hemoglobin, remember we said that it transports oxygen through the blood. So now how does the cooperativity assist in the function of the hemoglobin? You remember we had our state and oxygen. The orange state, very good combined with the T state. So we have so now let's imagine you're in the lungs, there's lots of oxygen there, right? So you'll draw in the oxygen. Each time oxygen it makes it hold more oxygen, more tightly. So it's will hold on to oxygen. Well, now let's
تعمل ايه؟
So there's very little oxygen. Oxygen comes here. And the oxygen starts to leave. And when the oxygen starts to leave, I do a conversion back to the T state, which has a much lower affinity for oxygen, and it dumps even more oxygen. Which is we want to move the oxygen from the lungs to the tissues. This is an example of how these special enable to carry out these functions in the organism that has very specific needs to interact with this environment, to maintain itself. So, how can we model cooperativity?
Oh my God.
Wow.
Wow.
يقول له ايه؟ يقول له ايه؟
The function of the body is like the when we have very strong cooperativity, takes on this form. We have in the numerator the dependence on the concentration of substrate to the end hour, and we have the same thing with the denominator. So this is when we have 0 substrate, fraction 0, and the substrate reaches very large. Now you say as it approaches
كده مش كده والحمار يدوم قطع المنطقة بتاعه يا جماعة
جامدة جدا.
which is X.
عاوز ايه؟ عاوز ليمون.
And so I have a very narrow range of X in which transition.
تدور وتعمل.
Almost like patience. Go
يا حبيبي
say. And so this expression is called.
رئيسه ايه؟
And as I say, it's an approximation of a very strong probability. But we can model probability by changing the standard. So the higher the n, the greater the probability. So for a small n, I'll get something that looks more like that. And then as n increases, I approach a much sharper curve. Okay, so I wanted to show you the Okay, here's it's not all but common reactions we have in biology. So for example, we have the fusion which quite similar to the previous example. This. And so we have these now as tools we can use when we have our networks, where we have lots of different reactions connected together. And each of these reactions can be described or approximated by one of the expressions that we used. Okay, so now we've been looking so far on, for example, the rate of production, the rate, let's say, not the part, or the rate
الجنون هتشتغل
of concentration. But there are a number of other ways to represent these network behaviors. And one of the very powerful ways, which would be familiar to anything that we do, then doing is placement analysis. So in placement analysis, we reactors are rather than with respect to time. And we look at the evolution in the phase plane. So let's take an example here. This is a network in which we have two reactors, S1 and S2, and each of them has a production rate. But we also have the conversion of S1 to S2, and S2 is an inhibitor of the reaction that creates S1. So just as a inhibitor, we don't expect to happen.
والله القعاد قدام البحر بحس من النفسية. أنا وأختي قدام البحر. أوديكم فين تاني؟ روحت امتى عندي بقى؟ روحت امتى؟
Steady state will have one S1 or one S2. S1. Why?
أنا مليون. كل ما يجي أسلم على حد يوم واقف. يا عم سلم أنت واقف. مليون أنت قاعد سلم خلاص. أنت بتحط. طب بتحط اللي قدامه. يعني من هنا أنت عارف كفاية كده لقيت واحد بيقف. يعني نص قاعدة كده.
Okay, so we
لقيت تبص على فوق المرة.
So differential equations, we have first order reactions. So we
يا مين أنت بتخوفني؟ خوفني. ليه هي بتخوفني؟
Remember we have march inhibitor. This S2 is inhibitor. Remember we have question.
يعني لا هو مش قصده حاجة بس فعلا يعني.
And so we set our equations.
يعني واحد وكده وفجأة يرجع بسم الله ما شاء الله يعني.
لا بقى وكمان الموضوع عمل ساتر قال لي بعتلي يودي الجامع بقول لك الموضوع مخطط.
لا مش الدرجة دي. انا كل الوعد هيبقى معاك.
لا عشان هو قلت له هبعت لك
يعني مش ده.
والله واحده بقيت له يعني
طبعا
كمان بعد
لا وانا ممتاز انا حصلت لي مره. معايا 6 أنصار جنبي. ساعتها انا مش مركز ولا حنيفه اللي بيلبس الكراتين. خلاص يا عم خلاص. يا حبيبي هنشيلها خلاص. يخرب بيتك.
Concentration in S2 versus concentration in S1. And so what we see is in the beginning,
بتعرف حد بتعرف مين؟
it's 1. So this slope
يا رفيق الواد اللي كان هيستفيد من الفيك
is going up past the S2. But then we reverse direction and it's 1.
مصطفى
Now that's
استمرنا
for
علي.
one particular set of
هو ده
that's for one particular set of
قابلته امبارح
initial conditions.
قرر.
Now for other sets of initial conditions,
انا بطلب واحد
we
السلام عليكم السلام. مش عارف مين
so
قلت له والله ما اعرف. انا كنت معايا في السعوديه ولا حاجه. ده دفعتي
بس
تمام. قلت له لا لا ما عارف حاجه. مش قبل كده قبل السعوديه ولا حاجه. قال لي انا في السعوديه بتاعك اهلا وسهلا بك. بالظبط قلت له لا والله مش عارف يعني بحب ايه. بس جاي من السفر مش مركز قوي. قال لي انا ايه صاحب على السبت بتاعته زمايلي كلهم. انت عارف مع ماجد برضه انا قلت له طب تقول لي انا ما اعرفش انت سعيده وبتاع وهات بوسه وبتاع هو خلاص تمام الامور طيبه. وتبقى طب اسم عشان ايه؟ انا قال لي بقول لك الدفاع محمد الدفاع اهلا وسهلا معلش بقى انا مش واخد بالي. قال لا ولا يهمك اتفضل روح خلاص انت روح انت بتاع
it's giving us
تحيات. وقعدت اقول ايه علي عصر دخلت على علي اشوف الاسماء لما جه محمد الدفاعي
what's interesting about
كان متجوز من زمان انه معاه عيله وقفل
what's the difference to us is
احنا قاعدين لا احنا قاعدين كتير مش عارف كيف ازاي لا هو قال لي وهو لقيته بيقول له غدر عمال قلت بقى المفروض
افتكرت قوي يا ماما ان الدكتور يا ابني تعالوا
ما تطلع يالا ما يطلع يا دكتور ما نمشي بقى ان شاء الله.
عايزين نعمل ايه؟ لا
هخلص بقى بكره مش عارف. كنت عاوزه ترجع.
Further analysis, we can draw
استغرب لو بسلم عليا وابوس بقى وبيتك عليه ده اتحرك.
in which I have either the arrow going. So these are the points where one word
ده بالبيت اللي هو ايه
فهمت.
and the point where the two not on a particular set is the steady state. Because that's the point at which I have zero movement and you feel the horizontal.
سلمى كل يلا كل يلا ها هذا هذا
ازاي ده كنا قاعد والله العظيم
لا كنت في الكلام ده كانت ما كانتش شايف على الاكل ده ليش تقدر تاكل بالاكل وتيجي تكلمني على اساس ان انا كنت الاكل
انا عندي حته كده انا لو فضلت جعانه طول العمر ما عنديش
ولا
لو معايا حد لا لا زي عارفه اللي هو متوفر
تخيل بيض بتاكل
لا ربنا
ده ما بتجيليش اكل معاك عشان السندوتش ده
Another dialogue.
ده بس لا
تعال كل ماما
I don't know if I maybe linked up to the wrong,
لا لا كنا شايف الورقه تحت
okay, so
بس انا والله العظيم فوق ما عارف انام والله ما عارف هموت وانام عاوز انام هو انا هناك مش عارف انام انا هناك برضه يعني وانا هناك
okay, so now let's make a base where we have condition both pathways.
اقرا من كده
Each pathway is enough.
انا
So now this is what our expressions look like. Now we've eliminated that error between the calculations. So we're just going to have a mutual information. And we have now probability. So we raise this term to the 10th power. And we have n1 and n2 because we don't necessarily have that same probability for the two conditions. Okay, so first we'll make a case in which we have what's called unbalanced division. In other words, this.
I sort of clear the model of it, in the same model we use where it is.
Okay, it's a good question. So what we've already seen, I think, is that there are very specific mathematical expressions, differential equations, which give us very specific kinds of outcomes. And we've also seen for a given pathway, and that pathway model may be based on, for example, an inequality pathway or a expression pathway. We still observe experimentally, for example, the product of one, let's say, for example, the one that produces amino acids goes into another path that produces proteins, or different precursors of glucose. For example, we'll go into that pathway that will eventually lead to the production of glucose. We'll break down glucose. Okay, so those are the things that determine how we know the arrow diagrams. You see how from the arrow diagram make the differential equations, and then we see where that is. Now the other approach may be if you observe for your network, and you know what kinds of mathematical expressions to produce that data, and then you try to figure out what it is in the system, what it is in the system, use the type of error diagram that we need for those equations.
So I can go on to this. An expression that should be able to listen to the end of so let's see we have the other maybe.
Yes. Yes, so you remember we said at the beginning that we're involved in reverse engineering. We have a system that we know how it's put together. So we have to do some law. And now what we're doing at the moment, we're just introducing the subject, is we're getting ourselves used to looking at different systems, looking at different models, looking at different sensitivities, and seeing what kinds of behavior they produce. And when we start seeing those behavior of biological systems, we'll have some idea of how to model. Okay. So, getting back to the system, now we're going to start out choosing our parameters so that we have unbalanced inhibition. In other words, the inhibition of one is stronger than the inhibition of the other. So, we're going to set A1 to A2, so we're a function of the food is its name, and we're going to set the big A1 to the big A2. So, it's A, right? So it's A, but we're going to set N1 equal to 4 and N2 equal to 1. So we just have cooperativity for N1. N1 represents the inhibition of S1 by S2. So that inhibition is stronger than the inhibition of S2 by S1. So what do we expect to happen? Yes, inhibition of S1 is stronger than inhibition of S2. Yeah, we expect that we're going to wind up with predominantly S2. Actually, I had the. So what we see is this is volume versus time for two different initial conditions, two different starting values, S1 and S2, and they both come out to the same time, which is that everything increases S2. And here's the phase curve. So in the phase curve, you can see that we have trajectories that are all coming to this point on the y-axis. The y-axis is S2, so we're all winding up with all of this. But now, what happens if we have balanced inhibition? Suppose we have the same degree of cooperativity in the inhibition of both reactions. Right? Okay, so that maybe there will be a steady state in which we have one is in and out. It's one S2. Maybe you guys agree? Okay, let's see. Okay, so here's two initial conditions. One initial condition, we started out with more S1 than S2. And we want to put all S1. And here's an initial condition in which we started out with more S2 than S1, and we want to put more S2. Yes, so if on the other hand, we started out with S1 equal to S2, then what would happen? So let's look at the phase. So here are our trajectories, and you see that we have trajectories. If we imagine the diagram going along here. If we're on this side below the diagram, that means that we started with more S. Then we started with more S1 than S2. Okay, and you see what happens. We wind up going to all S1. And also, if we're above the diagonal, that means we start our north to the next one. And you see all the therapies go to the y-axis, which means that we have all S2. Now draw the null points. So here's the null point for S1, the null point for S2, and they converge at these two steady states that we identified. So they converge another place. So what's happening in this other place? We have a third steady state. That's the steady state, which S1 is S2. Now, so this is an example of biseability. We call each of these steady states the basin of the function. So this line goes along the diagonal that separates us from the two domains. It's called the separators. And the final state depends on the initial conditions. So we got three steady states. Is there something fundamentally different about this steady state as compared to those two? Okay, so the difference actually is stability, right? So if I'm at this point, if I decide to move away from it, I'll be moved back. If I'm at this point and I decide to move away from it, I'll be moved back. But if I'm at this point, and I decide to even just tiny bit over to this side, I'll go to here. And if I move just a tiny bit upwards, I'll go up to there. So these are stable steady states. This is an unstable steady state. So if you look at it up close, you can see that very clearly. See, if I'm right here and I deviate it all, then I wind up going one steady state to the other. So you can think of this as the analogous to stability. You can think of this as being analysis to stable points and unstable points on the surface. And since we're working with networks, eventually we will look at systems where there are a lot of different variables. So it's very much a multi-dimensional, very high dimensional space. You can also have satellites, right? Where you may have stability with respect to one variable, or with respect to another variable. We have an incident. So that's what's being illustrated here. So we have a minimum, we have a state minimum, here we have a satellite. So then this stability becomes it's something interesting. So it's useful for us to be able in a baseline to stability and instability. And so this brings us to stability analysis. So with stability analysis, so we may have a set of that set up a very complex system. And it would be very difficult for us to solve it completely. But for any given condition, any given initial condition, what we're interested in is what's the direction of errors. Because depending on the direction of errors, we're very quickly going to get another set of conditions, another set of values for parameters, because you're gonna have a different solution. Right? So what we really want is in our planning, we can identify what the directions are, and also the points where we have steady states, and in particular the stable steady states and the unstable states. Okay? So all we need to know, we don't need to have a whole solution that the base case. We just need to know what's the derivative. Right? We need to identify the cases with the derivative is 0, and then we need the second derivative, right? To see whether it's stable or unstable. So we can just to simplify that, we can take a linear approximation. We can define our function of that describes, let's say, a concentration of one element in terms of the value of the function at that point in base space. So that's represented by S1. That's a very specific point in space. X. And then we can assume that we have a linear function where we just have the inaccuracy. We, for very small displacements, we have this derivative times S minus S1. Okay, so we write this equation. So let's say we have multiple variables, and that means we need to have multiple terms, linearized terms with the slopes. So we may be looking at that. We have two variables and there are two functions. When we're looking at the tangent plane. Right? So here are x, our x's, for example, might represent the primary change of the first substance, and then we might similarly equation for the time rate of change of the second substance. Okay, so we write down our linearized equations here. I notice that this is something in this case where we have two variables. We could actually write this as a 2x2 matrix equation, right? So we could have a vector that has our S1 minus S1 bar and S2 minus S2 bar. And we can have these four derivatives, these four partial derivatives, as the elements of our matrix. Okay, so now let's just do a simple change of variables. So we'll define x1 and x2 as just our small displacement from our initial position. And so we're getting something that you see here. Looks like the matrix equation. And then we can diagonalize the matrix in order to find the positions where we get solutions, where we get solutions of the matrix equation here. That will be where we have our series. So where we have our steady states. And in general, for these linearized equations, different. So if you recall from your differential equations, like it's called you guys differential equations probably at some time. You can get solutions that are exponentials, and you define these variables lambda, and then you can solve. You wind up with this quadratic equation, and you can solve that. And depending on what kind of solutions you get, you'll get different kinds of behaviors. So the eigenvalues, in this example, where you have two variables, you get two eigenvalues. And if the eigenvalues are both negative, then you just get exponential decay. Right? If the eigenvalues are both positive, you get divergence. Okay? So with the negative eigenvalues, you have a stable steady state. With the positive eigenvalues, you have an unstable state, which is leading to divergence. And if one eigenvalue is positive and one is negative, then you have a saddle. Now, this is all assuming real eigenvalues. If you have complex eigenvalues, then what happens? Sorry?
Imaginary part.
Yeah, so what does the imaginary part give us? The imaginary part will give us e to the I times x. That gives us sinusoidal functions, right? It gives us oscillations.
Periodic
Yes. Periodic function. So if we call the real part alpha, and we call the imaginary part beta, then the imaginary part will determine the frequency of oscillations, and the real part will determine the amplitude of the oscillations. And so if the real part, if the alpha is negative, of course, then the amplitude of the oscillations will decay, and we'll have a spiraling in behavior. And if alpha is positive, we'll have a spiraling out behavior, because we'll be seeing the amplitude of the oscillations getting larger. And the sign, the beta, will determine the direction of the oscillations. Okay? So let's look at some of the phase coordinates. So here's a system which involves positive feedback. So it's just very simple. Just three reactions, and all three reactions are irreversible. But because of the positive feedback, so if we think about it, if you have positive feedback, then as you start to increase the amount of S2, then that will cause you to produce even more S2. And so you get okay, so you get damped oscillations, then you will wind up with a solid curve, and that gives you a spiraling in, and that takes place with the parameter values that have been shown here. So K0 is 8, K1 is 1, and then the big K1 and K2 are 1 and 5. And we have cooperativity 2. So that's a relatively small amount of cooperativity. And this gives us the spiraling oscillations. And on the other hand, what happens if we have strong nonlinearity? Okay, so this will lead to sustained periodic behavior. But now, if let's say we have an imaginary eigenvalue, and the real part of the eigenvalue, the alpha, is 0. That means that we're not going to have a spiraling in or spiraling out. We just have a repeating oscillation, and that's when we have the limits. So what's happened here is that we have a spiraling in, but once we get into a particular region, then the solution of the equations becomes purely imaginary. Alpha goes to 0. And then you just have the limit side. And now if you're inside here, if you're inside that circle, then notice you're getting spiraling out. Because there the solution is giving you a positive value. Okay. Sorry? Okay, we'll get to that. All of these have been chosen from biological examples, actually. Okay, so this is just an example of spiraling out. Okay, so in general, what are the kinds of characteristics of and this fits to your question on how you do the model. What are the kinds of characteristics of the mathematical system that would give rise to these different behaviors, in particular oscillations? And there are basically two types of oscillators. They're called delay oscillators and relaxation oscillators. Delay oscillator takes place when you have negative feedback, but it's slow. Okay? So if you think about that, you'll be producing the reaction will be going in a particular direction, and it takes a long time, but eventually you get negative feedback, and this will send you back to your stomach. And the other type of oscillation comes when you have positive feedback, it's fast, and negative feedback is slow. So you can imagine positive feedback sends you more in this direction until you get the negative feedback. And this kind of oscillation gives you a pulse-like switching. It's not as smooth an oscillation as the other. Okay, so now what about situations? We see now examples where you can have multiple steady states. How do you identify and characterize those situations? This is called bifurcation analysis. And how are we doing here tonight? We have what, about 21 minutes? Okay, so I'll try to do this very quickly because we want to see biological examples. So here's an example in which, depending on the value for the rates, we could either have this simple steady, this simple behavior, where we just have one single steady state for each initial condition, or we could have a region. Now we're plotting against K1, which is, I think, this rate. And we find, so this is going to be where we have a fixed concentration of K2, and then we vary K1. So for very low values of K1, we just get one stable steady state. And notice that is a state in which the concentration of S1 is very low. Okay, but now as we increase the K1, this is versus small K1, so it's actually the reaction is producing S1, we come a very large K1 to a steady state that has very large values. And the more we increase K1, the more that increases. But in between, we have this bifurcation. We have two steady states in that region. And here we have the plot, the phase portrait at these different values of K1. So the first one, K1 is equal to 10, is here. And the second one, K1 is equal to 16, is here. So that's where we get the bifurcation. So you see that there's two places where the two null lines intersect. And same here, where we have K1 equal 20, this is K1 equal 20. So again, we have 2 points of intersection. And then here, where K1 is 35, we're up to this region where we just get 1 intersection. Okay? And in this case, this is going back to our linear pathway example. And we vary the inhibition. This is n. This is the exponent, remember, in cooperativity. So we're increasing the amount of cooperativity in inhibition. Once we go past about 2.4, then we get a bifurcation. And the bifurcation gives us one unstable steady state or a limit state. And the limit cycle you see is going from this point to that point. And as we increase the cooperativity, it becomes a larger amplitude oscillation. Okay, so sensitivity analysis is something that you'll find a lot of in the systems biology literature. This is where we look at defining how the steady state concentration of one component will be affected by changing the steady state concentration, by changing the initial concentration of another. Okay, so in other words, how sensitive is one step in our pathway to some kind of alteration of another step in the pathway? And that's something that's very important in metabolic analysis. So this shows an example for Michaelis-Menten case, where we're looking at the slope, the dependence of S on V max. And you can calculate that by rearranging the Michaelis-Menten equation to get the steady state value of S as a function of V max, and then just taking the derivative. And you wind up with this -3 divided by V max minus 2 squared. Okay, so relative sensitivity, that's just a means of normalizing the sensitivity. Then in the literature, people define some sensitivity parameters, very specific sensitivity parameters. So if you go into the literature, this is just so that if you go into the literature and you start seeing these terms, you have some idea of what it is. So you've got concentration control coefficient, is just defined in this way. It is the degree to which the concentration, steady state concentration, depends on an enzyme concentration. Flux means the flux, the rate of production, how that depends on the enzyme concentration, and so forth. It needs to be defined for every enzyme, let's say, in the pathway, and every substance. And of course, all of them will be a function of the different conditions. And you don't have to calculate all of these separately because there's a theorem called the summation theorem that says the sum of the control coefficients add up to 1. And I won't go into the proof of that. Because we want in the last few minutes to see some biological examples. Okay, so first, so the examples I'm going to look at are going to be from gene expression. So from gene expression, there are a number of different forms we observe in gene expression. So remember, we have RNA produced off of the DNA, and then protein produced off of the RNA. And the most common step for regulation is the production of the RNA. That takes place by an enzyme RNA polymerase. So that enzyme has to recognize the position of the DNA called the promoter, which is upstream from the coding region. And then you have the polymerase moving along the DNA and producing the mRNA. And then you have the ribosome jumping onto there and producing the protein. So this is if you have no regulation. But some of the common types of regulation include repression. So that's where you have some kind of separate element that can bind to the promoter and prevent the polymerase, for example, from binding, or just make it unproductive. So this will repress transcription, and you can also have activation. Okay, so if we think about how to convert this into differential equations, these different types of regulation, repression, activation, and combinations thereof. That depends. I mean, you can have repression or activation is cooperative, or it might not be cooperative. And it could be highly cooperative or just violently cooperative. Okay, so we could have activators and repressors. We could also have multiple transcription factors. We could have two independent factors, but we could also have two factors with cooperativity, or any number of factors with cooperativity. And we could have two repressors, or two activators, or a repressor and an activator, and so forth. And I think we all know how we would construct the differential equations for each of these situations. So, for example, to start out with unregulated gene expression, we have the rate of production of M. This is M for mRNA, this is RNA is called. And there will be a rate of production. And then we have minus delta M. This is the rate of degradation. And then there's the rate of production of protein. There's a first order term that depends on the amount of mRNA. This protein is produced off of the mRNA. And then we have a rate of degradation of the protein. So in this case, it's very easy to get the steady state. The steady state is when the derivative is 0. So the steady state concentration of the mRNA, for example, will be K0 over delta M, which makes sense because K0 is rate of production. So if rate of production is large, you wind up with a large amount of RNA. And if the rate of degradation is large, then you will have less. Okay, and then you can get also the steady state concentration of the protein, which is going to be dependent on the 4 rate constants. And then you get this parameter alpha. This is the overall expression rate, which comes from the rate of production of the protein. Okay, but you could also have the degradation of the protein here. So let's anticipate some of the other kinds of scenarios, how we would handle it mathematically. So let's say we have a transcription factor binding, then the rate is going to depend on the fraction of bound operators. So if we have lots of binding sites, then the fraction of bound operators is the concentration of bound divided by the number of concentration of free and concentration of bound. And now, if you have association constant, then you have dependence in this occupancy on the dissociation constant and on the protein concentration. So now the rate of activated transcription is going to depend on alpha times the fraction. Okay. And the rate of activated transcription is going to depend on fraction multiplied, and the rate of repressed transcription is going to depend on the fraction unmultiplied. Right? Because in the case of repression, the expression is coming from the unoccupied operators. And then we can go through this process if we have multiple transcription factors. And then it turns out that our expressions are going to depend on both binding constants and the concentration of both transcription factors and also the product of the concentrations. Okay, so you have the fraction that's unoccupied, the fraction in which just A is present, the fraction in which just B is present, and then the fraction in which both A and B are present. And then which one of these expressions comes into the rate, which ones we add together to get the rate, and on which ones are active. So that depends on whether having these factors there is repressing or activating. So, for example, if we have two repressors, then only the unbound contributes. Okay? But if you have two repressors and you only have repression in both repressors there, then we also include the singly bound fractions. Okay? All right, so then to add cooperativity, we just have this KQ, which is this cooperativity factor. Okay, so if we have n identical cooperative factors, then we take to the n power. Okay, so there are a number of different variations here, auto activation, and so forth. So now let's look at a very specific system. This is page language switch. So this is a viral switch between two different modes, the lysogenic mode and the lytic mode. So one mode, the virus just sits within the genome of the host, and it just reproduces itself when the host reproduces. In the other mode, it turns on a very large amount of expression, and it basically first takes over the cell and eventually lyses the cell. That's the lytic phase. And so there's three genes, three operators that are involved, and two transcription factors. One is called CI, and one is called PRO. And one of them is repressor, and one of them is activated, and they're competing for these three binding sites. Okay? And the two genes lie on opposite strands of the DNA, so they are transcribed in opposite directions, back and back. And there's some overlap between these promoters in which both can bind. Okay, so first of all, the CI dimer binds preferentially to the first operator. And then once it binds, then there's cooperative binding that extends to the second operator. Okay, so now in the absence of any proteins there, there's strong expression of pro. And the CI promoter has only weak affinity for the RNA polymerase. So there's minimal expression of the CI. So the polymerase is going in this direction to produce pro. When the CI dimer binds to OR1, it inhibits pro expression. And so you start to reinforce the production of the CI dimer. Okay, and when it binds to the second operator, which remember there's cooperativity, so it has that tendency. Once it's bound to the first operator, then it upregulates its own expression by binding to RNA polymerase at the CI promoter, effectively increasing the affinity of the dominant site. So CI is an autoactivator. And when it's bound to the third operator, though, it blocks access to the C1 promoter. So it then becomes a repressor of its own expression. Okay, so at high concentrations, it becomes an autoinhibitor. So we're having both positive feedback and then slower negative feedback. Okay, so the pro dimer is bound to the third operator, it blocks the CI promoter, so it inhibits expression of CI. But when it's found one of the first two operators, it inhibits its own expression by blocking access to the pro promoter. So it is also an autoinhibitor at high concentration. Okay, so we set up our differential equations. And okay, so we're almost out of time here. But we have now the rates for each of the scenarios when we have no bound, when we have CI bound at the first two places, when we have CI bound to all three, and so forth. For each of them, we have a rate of CI expression and a rate of pro expression, which we can substitute in our differential equations. Okay, and this is what we wind up with for the CI expression rate and the pro expression rate, and we don't really have time to go through and verify all of these numbers. We're just reading off of the table and substituting in the fractions that are appropriate. And here's the behavior that we see. Okay, so we have the two null lines, you see. One of them is solid, and the other one is gray. Both of them are solid. One is dark, and it's gray. And we have one. We actually have two. We have three intersection points here, here, and here. So we have bifurcation. We have one in which we have all CI, and we have one in which we have pro, and then we have this unstable. So A and B are for so with B you're getting another factor which is rep A. This is another protein that needs pro, and that shifts the overall curve. So now we just have the one steady state here. No, sorry, we said the rep A these seats above. Okay. So the last example, the second example here is actually from synthetic biology. So this is one which is a synthetic system in which we have two genes on two promoters, and each of them have a repressor, but each one represses the other. This is called the Collins toggle switch. And actually, you might recognize that this is very similar to the example that we've been looking at, right? Okay, so actually, we see base portraits like this before. Okay, so I think we're out of time now. I'm sure it's been 5 minutes. So, so thanks for our exclusive audience. Do you have any last questions? Okay, so if you have any other questions, you want to discuss systems biology, molecular biophysics, please feel free to contact me. Okay.
هو انا مثلا انا ما عنديش خبره في البيولوجي اصلا ما درستش كده. فايه ايه الصعوبات اللي هتواجهني لو جيت مثلا اعمل شيفت من الفيزياء العاديه للبايوفيزيكس؟
So what stage of your physics are you at?
لا لسه متخرج خريج السنه دي فيزياء عاديه سبيشال فيزيكس.
Yes, but are you in undergraduate or graduate?
I'm graduate.
Okay, so how many years of graduate study now? بدأت graduate study امتى؟ 2020